In this program, we're going to examine isomers more carefully. Let's begin by looking at some aspects of this flowchart. Some will seem familiar, some won't. First, isomers. Iso stands for same and mer, parts. So these contain the same parts, and we've translated that into meaning they contain the same formula. So far, we have examined what are called structural isomers. They have the same formula, but differ in connectivity. I want to demonstrate what I mean by that. Here are two molecules containing the elements chlorine, carbon, and hydrogen, the green being the chlorine. In the first molecule, the one on the left, I can see that the chlorines are connected to carbons 1 and 2, whereas in the second molecule on the right, they're both connected to number 1. So that is a demonstration of what I mean by different connectivity. We're now going to look at stereoisomers, and this will be a bit new. They have the same connectivity, but differing spatial arrangements. Let's look at what I mean by a spatial arrangement for a moment. Here are two molecules sharing similar connectivities. The chlorine is connected to 1 and another chlorine to carbon number 2. But they have a different orientation in three-dimensional space. These would be called conformational isomers. On the left-hand side, I've got another example of things differing spatially, but these would constitute what are called configurational isomers. Returning to the one on the right, these being called conformational isomers can easily be interconverted, meaning we change from one to the other, in this case by simply rotating. We don't have to break any bonds. Whereas the molecules on the left-hand side, we can't rotate. We actually would have to break bonds to turn it from one into the other. It's this configurational isomer that we're going to study in more detail. In our next slide, we're going to take a look at what are called cis and trans isomers, and in the next program, we'll look at what are called optical isomers. So, to demonstrate how cis and trans isomers arise, I want to look at a couple of requirements and these molecules that I'm presenting here on the right-hand side. The first requirement for cis-trans isomers is they require a bonding arrangement that doesn't allow any rotation. Things which are bonded in double bonds, you can't rotate them without breaking one of the bonds. And similarly with cyclic compounds, you can't rotate those without breaking a bond. So the one that can be removed is the one in the bottom right corner. With only a single bond, I can easily rotate that. The next criteria has to do with what's arranged to our carbons that are on either end of the double bond or either end of the section that can't be rotated in the case of a cyclic compound. R1 cannot be the same as R2, nor can R3 be the same as R4. Examination of our molecules on the right-hand side indicates that the remaining molecule on the right would violate this condition, so it can't have cis or trans isomers. That leaves these as two possible candidates. Here I'm providing the cis-trans isomer for our cyclic compound. I'm going to introduce here a reference plane, which would be the plane of the cyclic ring. Here I can see the chlorines in the first molecule on the left are on either side of that reference plane, whereas in the second molecule, they both lie on the same side. When they lie on opposite sides of our reference plane, we refer to them as trans. This would be called trans 1,2-dichlorocyclopentane. The one with them on the same side of the reference plane is called cis 1,2-dichlorocyclobutane. Here's the cis-trans isomer that exists for the one in the bottom. Again, instituting my reference plane, I can see that in the first molecule they both lie on the same side of the plane, so that would be called the cis 1,2-dichloroethane, and the second molecule on opposite sides of the reference plane, trans 1,2-dichloroethane. Let's look at a couple of questions involving our knowledge of cis and trans isomers. Let's try naming the following. The first thing I notice about the molecule on the left is it's a 5-carbon chain, so I begin with pentane. Having a double bond in it, pentene. Numbering from the end closest to the double bond, pent-2-ene. Now comes in the cis or trans variation. Here's my reference plane across the carbon-carbon double bond, and I can see that the carbon chain extends itself on the same side. So this would be called cis, pentuene. The molecule on the right is a cyclic compound, cyclopentane, with both bromines lying on the same side of the plane of the ring. So this would be called cis-1,3-dibromocyclopentane. Here's another question. Which of the following would be considered cis-trans isomers? Let's go through the options, W and Z. Well, those are really the same molecule. All I have to do is take Z and flip it top to bottom, and it would be exactly the same arrangement. So that's not a cis-trans isomer. What about W and Y? Well, an examination of Y indicates that it has two groups that are the same on one side of the double bond. You can't have that to make cis-trans isomers. So anything with the answer Y in it, we can take out. And that leaves X and Z. An examination of X indicates the methyl groups are on opposite sides of the carbon-carbon double bond, whereas in the model of Z, the methyl groups lie on the same side, so it would be the cis variation. In our next program, we'll examine another configurational isomer, optical isomers.